today is going to be day 2 of Power Series, and we're going to kind of continue on this Taylor series adventure here. So what this says is that the sigma, okay, that means the summation, so we're adding up a bunch of terms, just like we had those strings of terms last class, from 0 to infinity. That means we're starting by plugging in n equals 0, and you're plugging in forever. And we have this a sub n, and then this is, again, that x minus c, where c is your center, and that's the whatever degree it is. So that is going to generate a series of numbers. So when you plug in a 0, right, we'll call that first thing when you plug in 0, a sub 0, aka what you get when you plug in 0, plus what you get when you plug in the first term, and then that's multiplied by the center, right, plus what you get when you plug in 2, right, the second thing, and that's going to be to the center squared, plus dot, dot, dot. And we saw this kind of last class. So this was our constant term, then we had a linear term, and our squared term, and our cubic, and so on and so forth. So this is called a power series, where we're increasing the power by 1 each time. And it's centered at c. We talked about that last class. And remember, that c is just some number, like a 2, a 4, whatever. And for a power series centered at c, one of 3 things is going to happen. It's either only going to converge at the center, okay, or there's going to be this range of values where it converges. So it'll converge for some value that's less than r and diverges when the absolute value of that is greater than r, or it's going to converge for everything, okay? So it's either going to converge at c, converge over an interval, or converge for everything. So that capital R there, that's called your radius of convergence. And then we're also going to have, oh, we'll talk about that in a second. So radius of convergence of the power series. Now, if the series converges at C only, so if it only converges at the center, then your radius is going to be 0 because you're only converging at the center. Almost picture it like if you had a line here, and so if you're converging at your center, if it only converges there, you don't get any wiggle room on either side, okay? However, if the series converges for all of x, then your radius of convergence is infinity because you'd converge for everything. Versus, say there was some range where you converge, that's kind of that second option. So say it was, I don't know, -1 to 1 is where you converge, then your center would be at 0, and your radius would be a 1. So your radius is just how much on either side of the center are you converging for. That's all you're doing there. Okay? So the set of values of x for which the power series converges is the interval of convergence. So in this little quick drawing I drew here, the interval of convergence is the whole thing. So here the interval would be -1 to 1, where the radius is just 1, but the interval is the whole thing there. So that's called the interval of convergence, okay? So we've got that, and this convergence and divergence business should sound a little bit familiar to you. It should bring back some Unit 8 memories. So that Unit 8, 2 of the tests that are going to be the most useful here are going to be, your ratio test is going to be first and foremost the one you're going to use a lot. I've tried to use the alternating series test on a couple of them, and it gets ugly very fast. So my big recommendation is that you're going to want to use that ratio test, okay? So find the radius of convergence and the interval of convergence. Be sure to kind of check out your endpoints for your things there. Okay, so that Unit 8, the ratio test. If you recall, your ratio test, that was the one where you had to take the limit, okay, as you approached infinity of the absolute value, and that's the one where you had to take that n and replace it with an n plus 1. Do you remember that? So you had to take n, you replaced it with an n plus 1, divided by the original. And a lot of times you had something like this B example, where when you plugged in an n plus 1, then you divided by the original, and you did the, oh, well, just change it to multiplication and flip it. So we have that, and then the goal of the ratio test is that you had to compare things to the number 1. So if it was less than 1, you converged. If it was greater than 1, you diverged. And if it equals 1, the ratio test was inconclusive. So that's just kind of a recap of your Unit 8 there. And let's take a look here. By the way, what's one big clue that the ratio test is a good candidate to use? Well, remember when we talked about factorials, we said if you see factorials, that's a big clue that your ratio test is a good choice. Okay? All right, so the ratio test says I have to take the limit, okay, as n approaches infinity. Now, some of you may be freaking out because you're like, whoa, 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 there's n's and x's. That's not a typo. We are going to be treating the x stuff just like a constant because that is just related to our center. So notice that this limit is where n is approaching infinity. So that's kind of what I'm messing with. And the ratio test says wherever you see an n, you replace it with an n plus 1. So this n factorial turns to n plus 1 factorial. And I'm multiplying it by x minus 3. That stays the same because I'm not doing anything with x. But this exponent of n turns to an n plus 1. Okay? And then it's divided by the original. So I'm just recopying the original there. Okay, so we have the absolute value of that. All right, so now I need to kind of clean that up. So this is going to be equal to the limit as n approaches infinity again. And now I need to kind of remember what I can do here and what cancels. So if you remember n plus 1 factorial, that means n plus 1 times n minus 1, until you get to times 2 times 1. So this actually takes out this entire thing, and that kills. Okay? So we're left with just an n plus 1 in the numerator there. And then remember, if it's the same base, the rule is that you subtract the exponents. So let's see, the same base. So it's going to be that base with whatever n plus 1 minus n is. Well, n plus 1 minus n is just a 1, right? So it's really x minus 3 to the first power. Now, I don't really need to write the first power, though. Okay, so I've got this. Now, this is kind of the tricky part, but once you do it a few times, you'll get used to it because you do it every single time. Remember, our variable, so to speak, is an n. This is going to be just some constant that's going to, go for the ride. So this can actually be factored out. And you're going to do this every time. And again, it's because we're messing with the n over here. We're not really messing with x. So that's going to be, that gets factored out. I'm taking the limit as n approaches infinity. And it's going to be this n plus 1. All right, now I can actually take my limit there. If I plug in an infinity there, infinity plus 1 is even bigger infinity. So I get infinity, right? So if I plug that in, I get an infinity. Well, infinity times some constant, right? Well, that equals infinity. And again, the whole point of the ratio test, sorry, let me scooch this up. The whole point of the ratio test was to take that infinity and compare it to 1. Well, I know that infinity is bigger than 1, even I know that. So I can conclude that this diverges by ratio test, right? Diverges by rat test. All right, I'll put the ratio because rat test sounds gross. Okay, so that diverges by the ratio test. And what does that tell me, though? Well, if it diverges, that means that there's no place, it's not good news for all values of x. So that means that my radius of convergence is 0, right? It diverges. It's not going to have a radius of convergence. And the only place where this is going to converge is going to be at the center. So the interval of convergence is not really an interval. It's just x equals 3. That's as good as you can do here. Okay, so now in this example, I'm going to use ratio test again. But now when I plug in an n plus 1 wherever I see an n, remember I have to divide by the original. So instead of dividing by the original, I'm just going to, multiply by the reciprocal here. So I'm going to start this one over here, and I'm going to say the limit as n approaches infinity. And it's the absolute value. Wherever I see an n, I replace it with an n plus 1. So I still have x plus 1, and then this becomes an n plus 1 up there, divided by, and it'll be n plus 1 quantity squared. And then it's divided by the original, and again, so I'm changing that to multiplied by the reciprocal, and that comes straight. If you're having trouble remembering your ratio test, you're going to want to reference that hot pink sheet from Unit 8, and I need that raised to the end. Okay, so we've got there. So remember, what we're doing here is now we have things with the same base. You subtract the exponents. So very similarly, n plus 1 minus n just leaves me with a 1. So it's this thing to the first power. So that's going to equal, I still haven't taken the limit, so I just got to carry that down. So it's going to be x plus 1 to the first power, so I don't really need the 1 there. And then when I do these, you're like, I can't cancel anything there, right? This is going to end up, if you FOILed that out, right, you wouldn't be able to cancel anything. So I just have to rewrite it. So I'm just going to recopy that there, and I'm still taking the absolute value. And now, again, this x thing, that has to do with our center, so that's a constant. We're going to pop that out front. So I've got x plus 1, and then I've got the limit, technically that's absolute value there, as n approaches infinity, and I've got this. So I want you to think about how you would take the limit as n approaches infinity of this. Okay, so to take a limit as n approaches infinity, you should be thinking of your horizontal asymptote rules there. Now, if you kind of FOILed that out, you'd get an n squared. So you have an n squared there and an n squared here, so it's balanced. So you'd grab the coefficients. In this case, it's 1 over 1. So I've still got this x plus 1, this absolute value there, and it's balanced, so this equals a 1. All right, and again, the ratio test says that I want to figure out what that is compared to 1. Well, I want it to converge, right? So I'm going to say I want this thing, I want to figure out where it's converging to be less than 1 because I want to figure out where it converges. Now you need to remember way back to like algebra 1 or 2 to figure out how do you solve an absolute value. This is the one where you need to break it up into kind of 2 steps. I'm going to flip this over onto the other page because I don't want to have to squish it. Okay, so to solve that, I'll just recopy it. So remember, this was my goal. I had this thing, and I wanted to figure out where it was less than 1. So in order to solve that absolute value, remember you make this a negative, so it's negative 1 less than x plus 1. You drop the absolute values less than 1, and you have to kind of break it into 2 parts. So you subtract 1, so you get a negative 2 less than x less than 0. This is my interval of convergence. As long as I keep my x between negative 2 and 0, I'm going to have that whole summation converge. Why does this make sense? Well, if you look back to the beginning, what was my center? If you look back, it was negative 1. Is negative 1 in the center of negative 2 to 0? So let's draw a little, like this is my visual. So if my center was at negative 1, now I got negative 2 and I've got 0. So if my interval of convergence is this whole thing, what is the radius of convergence? Well, from the center to the side, that's a distance of 1, right? So you've got your radius of convergence equals 1, okay? So your radius of convergence is 1 because from the center on each side you'd go 1, and that makes sense then that the interval of convergence is negative 2 to 0. And if you want to make yourself a little note that your center was at x equals negative 1, and you can get that right from the beginning of the problem there. Okay, so there's 2 examples.